Yo, yo, yo. At this point, we have learned how to differentiate polynomial functions, radical functions, rational functions, exponential functions, and trigonometric functions. The next type of functions we're going to learn how to differentiate are logarithmic functions. And we've waited to do this because we need implicit differentiation to do so. So, let's take a look. Given the function y equals ln of x, what we're going to do so that we can differentiate this is we're going to rewrite this in exponential form. So we have, remember that the base here is e, and so if we write y equals ln of x in exponential form, this really means e to the y power equals x. So this is equivalent to e to the y power equals x. It's an equivalent way to write that relationship. Anytime we have something in logarithmic form, we can put it in exponential form or vice versa. And once we put it in exponential form, then we're able to use implicit differentiation to differentiate this because we can differentiate exponential functions. So let's differentiate both sides with respect to x. So we have d over dx of e to the y equals d over dx of x. Now, on the left-hand side, remember we're differentiating with respect to x, and y is a function of x, so we need to use the chain rule here. The derivative of the outer function, e to the y, is just e to the y. And we have to multiply that by the derivative of the inner function. The derivative of y is y prime, or dy over dx, either way. On the right-hand side, the derivative of x with respect to x is just 1. So once we've differentiated both sides, we have e to the y times y prime equals 1. And remember, our goal is to get y prime alone, so we need to divide both sides by e to the y. So that gives us y equals 1 over e to the y. But ideally, we would have this in terms of x, because remember, y is a function of x. That would be ideal. And if we look at what we have above, remember, y was defined to be ln of x. The equivalent statement is that e to the y equals x, and we've got an e to the y down here, so we can actually replace that with x, because e to the y is equal to x. And so when we do that, we write this as 1 over x, and this is our derivative of the logarithmic function. So what we have is d over dx of ln of x is equal to 1 over x. This is a rule that we can use whenever we want to differentiate ln of x. We end up with 1 over x. Now, this isn't the only type of logarithm. This is a natural logarithm where the base is e, but there are lots of other logarithms. So let's talk about what happens if we have a different base. Let's consider y equals log base a of x and see how these calculations change. If we have y equals log base a of x, the equivalent statement in exponential form is a to the y equals x. And then again, we're going to use implicit differentiation to differentiate both sides. This is a to the y. The derivative of that equals the derivative of x. Now, when we differentiate the left-hand side, the derivative of a to the y is a to the y times ln of a. And then we have to multiply that by y prime, because remember, this is a composition of functions. The outer function is a to the y. The inner function is y of x, so its derivative is y prime. The right-hand side ends up being the same. The derivative of x is 1. And so when we get y prime alone, we have to divide by a to the y and also by ln of a. So when we do that division, we end up with 1 over a to the y ln of a. And remember, a to the y was equal to x, so this ends up being 1 over x times ln of a. So the difference here, when the base is not e, is that we have an extra factor in the denominator that's going to be ln of whatever the base is. So we can say d over dx of log base a of x, if we have a base other than e, is going to be 1 over x times ln of a. So we have these two formulas now that we can use when we want to differentiate logarithmic functions. I want to do two quick examples. Well, a quick one and a medium one, just so we can get a little bit of practice here. And then, of course, there are more video examples of worked out problems that you can check out as well. So let's differentiate a couple of functions. Differentiate. The first one we're going to look at is y equals log base 2 of x. All right. This is a base that's not e, so we've got to use the second formula. And so here a is 2, the base is 2. So the derivative of log base 2 of x is going to be 1 over x times ln of 2. So we just have y prime equals 1 over x times ln of 2, because the value of a here is 2. The base is 2. That's all it is. Pretty straightforward. Once we know the formula, we're good to go. Let's look at one more example that we want to differentiate. This one will be a little more involved. Let's look at f of x equals ln of x cubed plus 1. We want to differentiate this. We're going to need the rule that we learned about the derivative of the natural log function up here. But also we have a composition of functions, so we need to use the chain rule as well. So when we're differentiating, the derivative of ln of u is just 1 over u. So this is going to be 1 over x cubed plus 1. And then times the derivative of the inner function. The derivative of x cubed plus 1 is 3x squared. And we can make this neater by putting it all in one fraction. So we get 3x squared over x cubed plus 1. And that's it. That's our derivative. Not that bad.